Hey, Vinay, let's wait for others for 2 3 minutes, then we can start. Am I audible?
Yeah, yeah.
Okay, let's start. So today we will wrap up our descriptive statistics part. Okay. So I just want to know if you have any doubt. We can discuss that, right? So far we have discussed measures of central tendency, measures of dispersion, right? We talked about quantiles, right? In quantiles, like we discussed about quartiles, percentiles, deciles, and we talked about skewness and kurtosis as well, right? So any doubt in any of the topic, Vinay, Ashish?
Sorry.
I can hear you. Tell me. Yeah, because of tomorrow we'll be, I mean, from the next class we'll be starting the next important section, that will be the probability. Okay, and after that we'll be discussing the most interesting part, that will be the inferential statistics. But to understand that in detail, you will need all these things, right? You should know each and every uh, part of descriptive statistics. So if you don't have any doubt, we can go ahead. But I just want to ask one question, right? Uh, so what is the importance of knowing mean and standard deviation, and is it enough to understand a data set? Can any one of you answer? Vinay, Ashish, would you like to answer? Let me rephrase the question. So will it be enough if I'm giving you mean and standard deviation of a data set? Then can you make assumptions about that data set if with these two values? Okay, I guess no one wanna answer that question. It's okay. Cool. Let's start with the topics then. Okay. Yeah. Yeah. So in the last session, we discussed about skewness and kurtosis, right? So today we will solve some examples and we'll talk about skewness and kurtosis in detail, right? So all of you know skewness measures the asymmetry of a data distribution, right? Relative to mean. If you have any doubt, regarding the old lecture, you can stop me. So we talked about the three types of skewness in the last session, right? One of them was the symmetrical distribution, where we used to say skewness equal to zero. So in that case, what used to happen? We were having all the three measures of central tendency on the same axis, right? They were having the same value. Talking about mean, median, and mode here, right? Do you remember the distribution that we talked about? It was a normal distribution, and your mean, median, mode was in center. Around your mean, your distribution was exactly same, right? Symmetrically same, I would say. Okay. So, the general or the common example, right? So the theory behind the population distribution is, right? So if you plot something like heights of adult male, right? So if you plot it, you will find a normal distribution. So because it's a general thing, right? Most of the time, will follow. I'll give you the examples and how it is look like. I have a notebook prepared for you. Okay. So let's talk about the next type of skewness is positive skew. That is right skewed, right? So if we're talking about right skewed, so whenever you calculate it, right, using the formula, we'll talk about the formula. We have not discussed it in the last class, right? So you will find the value of skewness greater than zero. Okay. The identification that I told you in the last class is the right tail is longer, in case of right skewed or positive skewed distribution. Do you remember how this right tail looks like, or what does it mean? So basically, it means, right, you will be having high value outliers on the right side of it, right? And in this case, you'll be having the mean as the biggest value, followed by mean, median, and then mode. Okay. Example I gave you in the last class as well, income distribution, right? If you compare individuals from a company only, you'll be having a lot of folks that will be, falling in a normal range, but there will be some people, right, like CXOs, they'll be earning a lot of salary, right? So that's why they'll come as an outlier in the distribution. Okay. Any doubt here so far? Cool. Okay. And the third type was the negative skew, right? That was left skewed distribution. So in this case, you will be having skewness value less than zero. Okay. So here in this case, if you see the distribution, if you visualize it, right? So your left tail will be longer, right? More low value outliers, right? So in this case, your mean will be the smallest value, then median, and then mode. Okay. Example is like age of retirement, right? Because most people retired at a standard age, but some retired much earlier, right? So those some people will be in the outlier. Okay. Any question here? Cool. So let's visualize these. I think you guys are not getting the picture. I have a old PPT as well here with me. Let me open that and then we can visualize it. Right? Can you guys imagine now? Right? So this is our symmetric distribution, right? So here in this case, your mean, median, and mode will lie on a zero axis, right? And your distribution will be symmetrical around it. But here, if you see the right positively skewed distribution, the right skew, you will be having a long right tail, right? Because you are having outliers on the right side of it. Okay. And similarly, in the negatively skewed, the left skewed distribution, you'll be having a long left side tail where you'll be having the low range outliers, right? The example I gave you, the retirement age, right? Okay. So let's go back to our original PPT. I mean, today's current PPT. Okay. Yeah. So let's talk about the formula for skewness, right? We call it as a Pearson's coefficient of skewness. And as I mentioned in the last class, these things are very important for your data science or statistics interview. Okay. So how we calculate skewness? It's a very simple formula. Skewness is equal to 3 times mean minus median divided by the standard deviation. And you all are aware about the all these three terms, right? You know mean, you know median, you know standard deviation. Mean median we discussed in the measures of central tendency session, and standard deviation we discussed in the measures of dispersion session, right? And alternatively, we have one more formula that is known as Fisher-Pearson skewness formula. Okay, here xi is your individual data point, x bar is your mean of the data set, q and represent the number of samples or observation, and sigma represent the standard deviation. Okay, so let's solve some problems, right, using these formulas, and we will see like how these values are, how these formulas are helping us to identify the skewness. Okay, so first we will take example of a symmetric distribution where you should get your skewness value 0, right? So it'll be great if you can try it on notebook, right? Or on a system, right? You can just try to calculate it. So we'll solve it step by step, right? And we'll be using the first formula that we discussed. So we'll be using the Pearson's coefficients of skewness, okay, to calculate this. If you are with me, Vinay, Ashish, okay, good. So let's start with the first step, right? So what is the first step here? Right, we need three things to calculate our skewness, right? So first we will calculate the mean. You guys know, right? The formula is very simple: the total sum of your observation and divide by the total number of observation, right? So your x bar, we represent mean with the x bar generally, right? So it's the notation for your mean. Okay, so here we are calculating the mean for our data set, right? So if you see, we have elements like 10, 15, 20, 25, and 30. We are adding them up and divided by the total number of observation data 5 here. So we are getting mean equal to 20. Second step is to calculate the median. Okay, since we have odd numbers, right? We will have odd value. I mean, we have that central value available here. So you should remember, right? If it is an even value, what we used to do, we used to pick two central values, and then we used to take the average of both, right? So in this case, we have a central value. That's why we are taking it directly. That is median is equal to 20. Okay. Now let's talk about the standard deviation. Okay. So you remember, right? Standard deviation formula, right? Summation of your observation minus mean square divided by the total number of observation. That was for your variance, and then we used to take the square root of it. So standard deviation is nothing but the square root of your variance. Okay, so we are doing the same thing. So we have the mean value with us, right? So we are basically calculating your variance first, right? And then we are taking square root of it. So how we used to do it? Observation minus mean square plus observation minus mean square, and so on, right? And divide by the total number of observation here. And then we take square root to calculate the standard deviation. Okay. So finally, we are getting the standard deviation value at 7.27. Right. Now let's calculate the skewness using our Pearson's correlation formula. Pearson's coefficient of skewness formula. Right. So the formula right, is 3 times mean minus median divided by the standard deviation. Okay, just give me a second. Yeah. Okay, so let's calculate it. So, our mean and median in this case both are equal. So we are getting the zero numerator here, right? So the final value of skewness will be 0. So it means your data is symmetrically distributed. Okay, any doubt here? Ashish?
No.
Okay. So give me a second. Yeah. So let's move to the next example, right? Where we have skewness greater than 0, right? And here we are talking about the right skewed or positively skewed distribution. Okay. We'll follow the same steps, right? We have the data set 5, 10, 15, 20, 50 with us. Now, first of all, we'll calculate the mean, right? Using the same formula that we used in the last example, right? So your mean is coming as 20. Now, and in this case, your middle value, again, we have odd number of samples. So your middle value is 15 here, right? And we will calculate the standard deviation. That is nothing but a square root of a variance. And we will know the variance formula, right? So our standard deviation is coming at 15.81. Okay. Then we will calculate the skewness using the Pearson's coefficient skewness formula, 3 times mean minus median divided by the standard deviation. Okay. So it is coming at 3 times mean is 20 here in this case and median is 15. So 3 into 5 into 15 divided by 15.81 is almost equal to 0.95. So your value is greater than 0. So what does it mean? It means your distribution is right skewed. Okay. And if you see, like if we, try to interpret it, right? So high value 50 pulls the mean up, right? Making it greater than the median. Okay. So, because you guys know, right? As we discussed in our initial sessions, right? Your mean can be impacted by the extreme values. Okay. Because of the outliers, your mean can, you know, suffer, right? But your median will not suffer that much, right? So that's why we prefer median in that case wherever we have extreme values, right? Or another method can be we can remove those extreme values while calculating them, right? All of you with me so far?
Yeah.
Okay. So now let's move to the next example where we will discuss about the left skewed or negatively skewed distribution. Okay. Again, we'll follow the same approach. We have 5 samples. We'll calculate the mean, we'll calculate the median, and we'll calculate the standard deviation. Okay. Now, if you calculate the measure of skewness, right? So it will come at minus 1.11. Okay. So you can see, right? Skewness value is less than 0. Okay, it means your distribution is left skewed. Okay, so why it is happening? So as we discussed, right, initially in the initial slides, right, if you have outliers, or we'll not call them extreme values, we'll call them as the small outliers, right? Because if you compare it with your remaining data, right, it's quite big. I'm talking about 5, right? So your low value 5 pulling the mean down, making it less than the median, right? So we discussed two things if you remember. So for a positively skewed sample, your mean will be greater than median and median will be greater than mode, right? And again, for your negative skew distribution, your mean will be lesser than median and median will be lesser than mode. So same thing is happening in this case. Okay, you can see it clearly here. Your median is greater than mean. Okay, we don't have any repeated values. We cannot calculate mode here, but in general, it'll be like this one. Okay. Let's move to the next part. So let's say if you have a large data set, so it's not a large data set, but in real life you'll be having a large data set, right? So you cannot calculate mean, median, and standard deviation by hand, right? So how can we do it in Python? So let's go to our notebook and try to do it. Okay. 1 second. Let me share my notebook. Can you guys see my screen? Vinashish, is it visible? Okay. So first, let's see. I mean, we have already seen, but let's see them one more time. Okay. So your normal distribution, right, where you have a symmetric distribution, it will look like this, where your skewness value will be 0. Okay. Your right skew distribution will look like this. You have a long tail on the right side because you have extreme values in this case. And in this case, your coefficient will be greater than 0. Okay. And for your left skew distribution, you will have a left long tail because you have low value outliers, right? And the skewness coefficient will be less than 0. Okay. And if you see, like, sometimes your distribution may look like a symmetrical distribution, but you will have a slightly right, long right tail. Okay. So these kind of things, right? So if you see this thing visually, these two distributions, they're almost looking like a normal distribution, symmetric distribution, right? So it's difficult to identify it by eyes. So better to calculate the coefficient, right? So here I have summarized it, right? For your symmetric distribution, your skewness will be 0. It will be a bell-shaped curve, balanced tails, right? Like this. Okay. For a right skewed distribution, your skewness coefficient will be greater than 0 and you will have a long tail on the right line. Okay. For a left skewed distribution, you will have a skewness coefficient less than 0 and you will have a long tail on the left side like this. Okay. And for a slightly right skewed or slightly left skewed, you will have moderate skewness coefficient like greater than 0 or less than 0, depends on what kind of skewness you're trying to detect, and slightly stretched tail on the left or right side of it. Okay. So again, I just want to repeat it, right? For a normal distribution, you will have mean equal to median equal to mode, right? It may not be exactly equal, will almost be equal. Okay. And for your right skew distribution, your mean will be greater than median and median will be greater than mode. Okay. Example is your income distribution, sales data, and wealth inequality. Okay. And similarly, for left skew distribution, you will have mean followed by median and followed by mode. Okay. So it could be like found in exam scores. Most students perform well, but a few fail, right? So you'll be having that kind of left skew distribution in case of exam scores. Okay. Slightly right skew distribution, similar to right skew, but less extreme. Okay. Found in some financial data and business market. Okay. Now let's see how to, calculate the skewness for a large data set using Python. Okay. So consider this large data set as data here. Okay, and we'll be using SciPy library. Okay, so from SciPy library, we have a package inside the SciPy library, scipy.stats. We can import the function that is your skew. Okay, so here again, right? Uh, you can basically pass your data set directly to this skew function, and it will calculate skewness for you. Okay, but I just want to show you how to calculate mean, median, and standard deviation using the NumPy library as well. And because we have not discussed this in our initial session, we saw like how to calculate it using pandas, right? But in some cases, you have to calculate it using NumPy library. Let me tell you one more thing, right? When you do the operations using pandas library, they are comparatively slower than your NumPy library, right? So you can even test it. Take a very large data set, convert that large data set into array and try to compute the same things, right? And put a timer. Okay, you will see a huge difference between the time of calculation between NumPy and pandas library. Okay, so whenever you need fast computation, and generally we need it in deep learning and machine learning tasks, right? So better to use these things. Okay, so now let's print it mean, median, and standard deviation here after calculating it using NumPy library. It's very simple. np.mean, pass your data set, np.median, pass your data set. So it takes a list parameter. Okay, so your data set is list, right? We are just passing it as a list. Okay, so if you print it, mean, median, and standard deviation skewness, you can see it here. So mean is coming of 51.11, median is 50, standard deviation is 227. Okay, and skewness is 0.24. Now I want one of you to answer what does it mean? Right, our skewness is 0.24. So can you tell me what kind of distribution it is?
Right side positive.
Right side positive, right? Great. We can, again go up and check it as well. So if you see right skew distribution, skew is greater than 0. Okay, great. I think it means you guys understood, right? So will you be able to calculate it in future, right? If you want to do it using SciPy library?
Yeah.
Great. Okay, now let's go back to our PPT. We'll come to this notebook again. We have other things as well to discuss, right? Let's go back. Okay, and let me share the other screen. Okay, let me know if it is not visible.
Visible.
What you can see the notebook or the PowerPoint?
Yeah.
The which screen you can see? I'm confused here. PowerPoint.
Example for large dataset Python implementation.
Okay, great. Okay, kind. Well, so I've summarized all the four examples here, and we have already discussed these things multiple times, right? So let's move to the next section. Okay. So the second thing that we have discussed in our last class was kurtosis, right? And you know, like what is kurtosis, right? We used to measure the tailedness of a data distribution. You know, how much of the data is in the tails versus the center. Okay. So again, we are talking about the outliers here only. Okay, and the spread of your data set. Okay, so we discussed three types of kurtosis, right? One was macrokurtic, second one was leptokurtic, and third one was platykurtic. Okay, so what were the properties of all these three kurtoses, right? Let's discuss those in detail. Okay, so we discussed mesokurtic means normal kurtosis, where you will be having the kurtosis value 3. Okay, so it means moderate tilts, you know, like a normal distribution. Okay, example IQ scores in a large population. I'm taking example of a data set, the real life example. Okay, leptokurtic, where you will have high kurtosis value and kurtosis, if you calculate the kurtosis coefficient, will be greater than 3. We calculate this kurtosis value using a formula. I'll tell you the formula in the next slide. Okay, so in this case, your distribution will be having sharp peak and heavy tails. Okay, means more extreme values. Okay, examples like stock market crashes, frequent extreme losses in. Okay, third one is platykurtic, that is low kurtosis, where you'll be having kurtosis value less than 3. Okay, so in this case, you'll be having a flatter peak, light tails. It means few extreme values in your in that distribution. An example is uniformly distributed test score. Okay, now let's move to the formula. Okay, so here in this case, if you see the formula of kurtosis is this summation of your observation minus mean power 4 divided by n total number of observation into your sigma, it means your standard deviation time power 4 minus 3. So why are we doing this minus 3? It means you okay. So we just want to have the kurtosis value equal to 0 for your normal distribution. Okay, just to normalize it, nothing special here. Okay, it just makes interpretation easier, like your skewness, right? All of you understood? Any confusion so far?
No. Go ahead.
Okay, great. Yeah. So now let's calculate the kurtosis. Okay, I forgot to tell you. Yeah. So names. Here we don't have any special name. This is the basic formula here. Okay. So again, so we had like three important things here, right? Basically two. Okay, we have our mean and standard deviation, right? So in first step, we'll be calculating the mean for our data set. We have this data set here: 10, 20, 30, 40, and 50. Okay, so we can compute the mean, right? We know the formula for that. So it's coming as 30 here. In the second step, we'll be calculating the standard deviation. In this case, our standard deviation is coming at 14.14. Okay, then we will put all these values in our kurtosis formula. You know the formula, right? So it was summation of your uh, observation minus mean, right? And the power 10 times 4 divided by the number of observation and standard deviation time power 4 minus 3. Okay, here in this case, 10 is your observation, right? 10 and 30 is your mean. 10 minus 30 power 4 plus 20 minus 30 power 4 and so on. Below we have total number of observation 5, right? Into standard deviation, that is 14.14 power 4 and finally minus 3. So your final value is coming at minus 1.3. Okay. So here in this case, your kurtosis is equal to minus 1.3, indicating a platykurtic distribution. It means light tails, few extreme values. So if you remember here, we discussed if it is less than 3, right? Your distribution will be having flatter peak, flat tails. Okay, understood? So don't go with this mesocartic example. It'll be here and there. Okay, understood? Do you know how to use the formula? Okay, great. Now let's move to the next example where we are talking about the leptokurtic distribution. Okay, so similarly, we have this data set and we have one extreme value here that is 200, right? We'll calculate the mean using the same formula, total value of, I mean, the sum of your all the observation and divided by the total number of observation. Then we'll calculate the standard deviation. Standard deviation is nothing but the square root of your variance, right? And then we'll put all these values in our kurtosis formula. Okay, so your kurtosis value is coming as 11.7. Okay, and this kurtosis value is greater than 0. It means you know, right, what it is. It is a leptokurtic distribution. So what does it mean? Your distribution will have heavy tails and extreme outliers. You can see this outliers correctly, like here 200. So we are dealing with a very small example as of now, right? But in real life, we'll be having a very large data set where you cannot see anything with your eyes, right? Everything with your eyes. So better to calculate it using the formula. We will see how to, calculate the kurtosis using the Python. Okay, now let's move to the next example, right, where we have kurtosis value less than 0. We have already discussed one such example where we were getting the kurtosis value less than 0, right? So just to repeat, so if it is if the kurtosis value is less than 0, it means it is a platykurtic distribution, right? Your distribution will have light tails, fewer extreme values, right? So let's visualize this, using our old PPT first. Okay, let's move to the old PPT and let's have idea, right? How does it look like? So can you guys see, right? This mesocartic distribution, you don't have, a very sharp peak or extreme tails, right? It's a very smooth kind of a curve, right? A bell curve, right? But so here in this case, normal kurtosis is equal to 3, right? But we are subtracting minus 3 from our kurtosis formula. It means in this case, your kurtosis value will be 0 for your macrokurtic distribution. Okay. In case of leptokurtic, right, you will be having a sharp peak, right? And your extreme values, right? Heavy tails. You can see like this. We are having tails here. Okay, but in case of platykurtic, where your kurtosis value is less than 0 or less than 3, right, you will be having a flatter peak like this. Okay, and thinner tails, like we don't have any tails, like thinner tails, right? Meaning very few extreme values. Okay, so any doubts so far? Anyone? I'll take a pause of 30 seconds. If you have any, please let me know. Then we'll move to the next section. Okay, I guess no one has any doubt. Okay, thanks, Vinay. We can move. Yeah. Yeah. So now let's calculate kurtosis for a large data set using Python. Okay. So let's move to our notebook again. Let me share my screen. Okay. Let me know if it is visible for you guys. Is it visible? Can anyone tell me? Is it visible for you? The notebook?
Yeah, it's visible. Like, actually, screen, like, I have to zoom it and I have to see each and everything.
Okay. You can tell me. I could have zoomed it, right?
Yeah, can you please zoom it? Like,
Sure. Okay. Yeah. Is it fine now?
No, it's fine. I can zoom it from my end. I can see that in that way. Like if you zoom also, it is coming. It's over like it's pixel out, so I can see. I can do from my end.
Okay, great. Yeah. So we just saw, right, examples of all three types of distribution: mesochaotic distribution, leptochaotic distribution, and platychaotic distribution. Right? Even you can plot these kind of curves like this, right? So I'm using the matplotlib and C1 library, right? So I'm just creating them using the NumPy library, right? I'm just curating the data set, right? So I've just used numpy.random.normal to make a standard normal distribution, np.random.laplace, okay, to make a Laplace distribution. We will like discuss all these kind of distribution in our future further classes, right? So for now, just see, right, how these three types of distribution looks like, right? You already have the idea how mesochaotic distribution looks like, right? Right, it will look like this. It will not have any heavy tails, right? It will have a moderate peak balanced tails like this. Okay, for a leptochaotic distribution, right, where you'll be having heavy tails, kurtosis value greater than zero, right? So you will have a sharp peak and tails like this, okay, because you have a lot of outliers in this case, okay. In case of platychaotic, you will be having a flat kind of peak here, right, and very minimal tails, right, and your kurtosis value will be zero, okay. Same interpretation I mentioned here, okay. Now let's calculate it using Python. Okay. Similarly, same thing. I'm using the SciPy library again from the stats package. I'm importing the kurtosis function. Okay. So you can directly pass your data. Okay. It should be in a list format, right? If you're using this function, right? Pass your data in the kurtosis function directly. Okay. And it will give you the final kurtosis value. Okay. So I'm making Fisher is equal to true because in our case, we were subtracting -3, right? So it basically normalize it. Okay. So here in this example, our kurtosis value is less than 3. It means it's a platychaotic distribution. Your data set is having light tails. Okay. Any question, any doubt so far? Will you be able to solve, like, calculate kurtosis using Python? Okay, I'm taking this as yes. Let's move to the next part. I'm gonna share the PPT again. Just give me a second. I hope it is visible to all of you. Okay, so here I've summarized this, right? You guys can take 10 seconds and read it. If you have any question, let me know. And if you want to have any real world application, know about real world application or more code examples, I can share it. I mean, I can share that with you.
Yeah, show a few more examples.
Sorry?
Yeah, share a few more examples with us.
Okay, sure. I think we have already discussed few, right? If you remember, just give me a second. Okay. Yeah. So if you talk about a natural data set, right? So in general, like if we are plotting something or for the entire population, right? So let's say if we are talking about heights of every individual on this planet, right? If you plot that, so it will come as a normal distribution. So any data set that is having normal distribution, right? It'll be following the mesochaotic distribution. Okay. Now let's say if you are talking about the stock market crashes, right? Or financial risks, right? So how frequent are stock market crashes, right? Now all of you are adult, you understand stock market, right? So is it like it's a very rare thing, right? It will not be crashing every day, right? It's a very rare event. So it means it's an outlier, right? But it'll have some value, right? And whenever you like see the peak, right? So that even the peak will be kind of a sharp peak. Correct? It's going high. Financial risk, you can take this for an example, right? So in that case, you will be having a leptochaotic distribution. Okay. And on a plateautic flat distribution, you can take example of your scores, right? Generally, we get scores in almost similar range, right? So let's say the score, let's take example of 100 marks exam test paper, right? If it is a maths test in your class, right? Not talking about competitive exams, I'm talking about a normal exam in your class, right? So in that case, you will be having scores almost in a similar range. So in that case, your flat, the peak will be almost flat. Okay. So that distribution will be a plateautic distribution. You'll not be having, extreme tails in your in this kind of data. Any doubt? Any question? If you want, I can share some real world, applications or examples with you. I'll share it with Anuj. He will share it on WhatsApp. Is it fine? Yes. No.
Yeah, fine, but in case like any real time data set, if you show, it will be more like
So it's not handy with me right now. I can show it in the next class if you want.
yeah, next class is fine. Anytime is fine, based on your availability and things. But when
Sure.
it comes to real time, we'll get more confidence.
Yeah. Yeah. Agree.
Thank you.
Okay. So let's move to the next section. That is box plot and outlier detection. Okay. So it's a very interesting topic, right? And we use it almost, every time when we try to analyze our data set, right? To detect the outliers, right? There are a number of algorithms, right? But if you really want to see with your eyes, if you want to visualize it, box plot and Weiland plots are the best approach. But in this session, we'll be discussing about the box plots. Okay. So like how do we represent a box plot, right? There are few things that are required for a box plot. We will like see this in the visualization as well, right? So let's see. Okay, so first of all, you need the knowledge of our previous class that we discussed, right? So I want someone to come up and like tell me about what are the quartiles that we discussed in the last class. Anyone? You told me like you understood everything in the last class, so I want one of you to come up and tell me.
Sorry, a quartile, right?
Yeah.
Like n by the position, the calculation of it based on the position.
Okay. Can you like
P
try to
by
explain instead of mathematically explaining it? Can you try to explain it in a with example like how we do it, why we do it?
yeah, it based on 25 percentage or 50%, 75% thresholds. Based on that,
Yeah.
the way we calculate it.
Okay, great. So usually like what we do using the quantiles, right? If I talk about the broader thing, right? Instead of a quartile, type of a quantile, right? We used to divide our data set in some set of groups, right? So in case of quartile, we used to divide our data in four equal parts, right? So Q1 used to represent 25th percentile, below which your 25% of your data falls. Okay. Similarly, Q2 represent your 50th percentile, below which your 50% data falls, right? So Q2 is nothing but your median, right? As we discussed, if you remember the center point of your percentile, because in case of percentile, we divide your data set in 100 groups, and Q2 represents your 50th percentile. Okay. So here Q median Q2 is nothing but a central line inside the box. Okay. So if you visualize the box plot, so Q2 will be representing, or the central line will be representing your Q2 median in case of box plot. Right? We will visualize it. Wait. Okay. And the other two things will be in your box plot, right? The box edges. Okay. So the first edge will be your Q1, 25th percentile. Okay. And your last edge will be the 75th percentile. That will be Q3. Okay. If you have any doubt, stop me anywhere and ask it. Okay. And if you remember, you used to calculate the interquartile range as well, IQR, right? Using the IQR, we were detecting some outliers in the last class. right? So how we used to calculate IQR? It was the difference between the Q3 and Q1. Okay, we used to calculate the spread using this difference. Okay, any question here? Okay, no question. Okay, now the whiskers, right? I'll show you what are those whiskers, right? But they'll be, the value of those whiskers will be 1.5 times your IQR. So they'll be beyond Q1 and Q2. Okay, I'll show you like what are they. Okay, now your outliers, right? Because we are doing this exercise just to detect outliers, right? Data points outside whiskers are marked as individual dots, right? Or the outliers. We will visualize it. Okay, now let's try to solve it using a formula. Okay, so we have these test scores 4200. Okay, so our Q1 is nothing but 50. We know how to calculate it, right? If you don't know, please revise. Right, and the Q2 is 65 median, Q3 is 90. It's nothing but a 75th percentile. We know how to calculate it. We know the formula, right? We have discussed in the last class. And IQR is nothing but the difference between Q3 and Q1. That is coming as 40. Okay. So to detect the outliers, right? If you remember, right, we use lower bound and upper bound. Correct? So if any values fall beyond these, Q1 minus 1.5 times into IQR or Q3 plus 1.5 times into IQR, we call them as outliers, right? Now let's move to the next section. Okay. So we like before visualizing it, I just want to have some key takeaways, like how box plot helps visualize data distribution get outliers, right? So we'll be discussing that in our notebook. Okay. So one important thing, so your right skewed data, right? So if you have a right skewed distribution, your outliers will be on the right? In case of a box plot. Okay. So again, all these things that we have learned so far are helping us, right? This using just to, just a box plot, we can tell, okay, is it a right skew distribution or a left skew distribution? Because you can see if your data set is having outliers on the right, it means it's a right skewed data or distribution. If your box plot is having outliers on the left side, it means it's a left skewed distribution. Okay. And extreme outliers significantly affect the statistical analysis. That's why this exercise is very important, right? Outlier detection exercise is very important because if you build any machine learning model or perform any statistical analysis and your data set is having outliers, your final result will be biased or maybe wrong because of your extreme values. Right? So it's better to deal with the outliers before performing any statistical analysis or training any machine learning model. Okay. IQR is a standard way to identify outliers as we discussed in our last class, right? Okay, before moving to the Z-score, let's see how this box plot looks like. Okay, well, I'll take a pause here. If you have any question, please let me know. Meanwhile, I'll share my screen. You can ping me, guys, if you don't want to speak. Okay, can you see my screen? Can you see the box plots?
Yeah.
Okay, great. Cool. So if you see the first distribution, right, here in this case, we don't have any outliers. So it means it's a perfect distribution, right? Normal distribution or the symmetrical distribution that we get, right? So here in this case, if you see the center line, the center line is representing your median value. Okay. And the bottom and the top thing is nothing but your Q1 and Q3. Remember we discussed this? The box edges. Okay, and these things, these lines are the whiskers. Okay, and as we discussed, like if any value is coming out of those whiskers, right, we will call that as outlier. Okay, one or two is there, it's fine, right? but it's a perfect normal distribution kind of example. Okay, so if you see the next box plot, that is not, so this one is for your right skewed data. Okay, so similarly, this line is representing your median. Okay, and these two are your whiskers that we calculate using the formula, right? Remember how we calculate whiskers? 1.5 times of IQR, right? IQR is nothing but the difference of your Q3 minus Q1,
Uh,
right?
uh, Arshu, sorry to interrupt you. Can you please explain me box plot one more time? Sorry.
Yeah, sure. Okay, yeah. So as we discussed, right? So there are four important things in a box plot. Okay. First of all, we'll have a center line that is nothing but the median, right? And median is nothing but the Q2. Okay. And the box edges are nothing but your Q1 and Q3. Okay. So the bottom part of this, you see, this is nothing but this line. This particular node is your Q1. Okay. This line. Okay. This line is this edge is at Q1. Okay. The value if you see here, it will be Q1. And the next edge will be your Q3. Okay. And we calculate, and these two lines are represent nothing but the whiskers that we discussed, right? And how we calculate the value of these whiskers? It is 1.5 times of your IQR, interquartile range, right? And how we calculate IQR? IQR is the difference between your Q3 and Q1. Okay, it's clear
Yeah,
now?
got it. Got it. Got it.
Okay, great. Now let's see
Thank you.
this for the right skewed data or a right skewed distribution. Okay, so if you see here, as I told you, right, in case of right skewed distribution, you'll be having outliers on the right side of it, right? So we don't have any outlier on the left side of it. So if you rotate it, it'll be left or right sided. You can visualize it. Top is right and bottom is left. Fine. Any doubt here in visualizing left or right side of the box plot? Please, yes, no.
Yeah, go ahead.
Cool. Okay, so if you see here, we have outliers on the right side of the whisker. And again, they are outside of the whisker. It means this data set has some outliers. Okay. And it's a right skewed data. Okay. Now let's see a left skewed data, right? In this case, you will be having outliers on the left side of it, left side of the whisker, right? It's coming here. It means it's a left skewed data. You can easily visualize using the box plot, right? If you have outliers or not, right? Your values, your circles will come like this. You'll be having dots outside of your whiskers, right? If it is outside of your whiskers, then you can say, okay, my data set has having outliers, right? And if your data set has having extreme outliers, right, it will look like this. It will be very, very far from a whisker, right? And these kind of outliers are very dangerous for your analysis, right? Because right, when we were calculating mean, right, how it was getting impacted, right? We were having values ranging from 10 to 50, and when we add a value like 500, it changed the mean like anything, correct? So if you have these kind of extreme outliers, this will definitely impact your statistical analysis. Okay. So better to deal with these values before performing any analysis. So what could be the one solution? Okay, one solution could be drop these values, right? And then you'll be left with the values in the same range. Now you can perform an analysis, right? So in this case, right, in case of your normal distribution, right? There's no outlier, right? Data is symmetrically distributed and no extreme values beyond 1.5 times your IQR. That is nothing but a whisker. Okay. Any doubt in analyzing whisker, box edges, or box median? Okay. So second example was about the right skewed data, and you guys know, right, how to identify right skewed data. If you plot this distribution of your right skewed data, it'll be having a long right tail. Okay. And in this case, in case of your box plot, outlier will appear as dots on the right side of your whisker like this. Okay. So similarly, if we talk about your left skewed data, and if you plot the distribution of your left skewed data, it'll be having a left long tail, right? And in case of your box plot, you will be able to see dots on the left side of your whisker like this. Okay. And in case of the extreme outliers, right? So your extreme outlier will be very, very far from your whisker. It will look something like this. Okay. This means if it is very far, you can easily say, right, it's a extreme value. Okay. So will you be able to analyze the outliers in your data set using the box plot? Yes or no? And again, it's a very interesting question, right? And people like me generally ask this kind of question, right? How will you analyze the outliers using the box plot, right? Then you should that time you should know like all these terms, right? What are the edges of your box plot? What is the center of your box plot? What are whiskers, right? How we calculate whiskers, right? So if you are saying it's 1.5 times of IQR, right, then you should know what is IQR, interquartile range, right? How we calculate interquartile range. You should be able to say it confidently, right? It's the difference between your Q3 minus Q1, right? And then you should be able to explain what is Q3, what is Q1, right? Q3 is nothing but the 75th percentile, right? Q1 is nothing but the 25th percentile, right? And percentile is nothing but you're dividing your data set in 100 equal groups, right? So any confusion so far and in this understanding box plot or anything that we have discussed so far? Yes, no? Okay. I'm taking this as a yes. Okay.
Yeah.
So yeah. So now, like I've written this function, how to like detect outliers. So it's nothing. It's the same thing that we have discussed in our last class, the lower bound and upper bound. Okay. So even you can write a function like this. We can calculate Q1 and Q3. Q1, here we are calculating Q1 is using this formula. NumPy, we are using NumPy only, NumPy library of Python. NP dot percentile, we are passing data here and we are asking for the 25th percentile. Okay. So with the help of this, I'm teaching you how to calculate the percentile using the NumPy library. Okay. Similarly, if you want to calculate Q3 or any percentile to be fair, okay, you can just pass it here. 1 to 100, you can pass any number here and it'll give you that percentile. Let's say you want to calculate 10th percentile, 20th percentile, 99th percentile, right? Just pass that number. Okay. But for us, Q3 and Q1 is important because we want to calculate the IQR, right? And you guys know IQR is nothing but the difference between Q3 and Q1. Okay. So in the last class we discussed, right, how to calculate lower bound and upper bound, right? Lower bound is nothing but the difference of your Q1 minus 1.5 times your IQR. Similarly for upper bound, it's nothing but Q3 plus 1.5 times of your IQR. If any value is there beyond these two values, lower bound and upper bound, then we will call them as the outliers, right? It's nothing but a list comprehension, right? You can open this as well, right? I like to use shortcuts in Python. Okay, so here we are detecting outliers using a list comprehension. Basically, we are just checking if any value in your data set is greater than upper bound or lesser than lower bound. Okay, and I hope you have learned list comprehension in your Python classes, right? Okay, I'm taking this as yes. Okay, so let's print, right? I'm just calling this function detect outlier, and we are calling this function for all the four distributions that we have discussed, right? So if you call your detect outlier function for your normal data, right view data, left view data, and outlier data, the extreme outlier one, it'll look like this. Okay, so in case of your outliers normal data, one very small value that was coming here like this was there, right? Okay, but in your right view data, we were having multiple values like three values. Okay. And in your left script data, we were having in 4 5 values. These are coming like this. So you'll get all the values right here. Right. And in the extreme outlier section, you were having these three bigger values. Right. So these are those three values. So that's how you will be able to identify the outlier from it. Okay. Any questions so far? Cool. Okay. Let's go ahead. Okay. I'm moving to the,
Yeah. Next.
yeah.
Yeah, it's good.
Okay. Is it visible to all of you?
Yeah.
Cool. Okay. So now we have one more important concept, that is z-score. Okay, z-score is a very interesting concept, right? So now, like, okay. So let's say if I'm giving you a value, right? And now I want to know like how far or how many standard deviation away is your value from the mean. Okay. So how will you calculate it? So the formula is, so we call it as a z-score, and we will again like talk about it in future, right? When we'll be discussing the inferential statistics. Okay. So the formula for z-score is x. X is nothing but your data point, the data point that I'm giving you. Okay. I the question that I mentioned initially, right? I want to, know how far it is, like how many standard deviation away this value is from my mean. Okay, so the formula is x minus x bar. X bar is nothing but your mean divided by the standard deviation. Okay, so again, uh, interpreting z scores. Okay, if z value is greater than 0, it means value is above the mean. Okay, if your z score is less than 0, value is below the mean. Okay, if z is greater than 2 or minus 2, it's a possible outlier. Okay, so again, it helps us, to detect the outlier as well. It has a very good significance in machine learning, right? We standardize our data using these, and we will definitely talk about it in future. Okay, so now let's try to solve some examples using the z-score formula. You know, so let's say I'm giving you two things for the test scores, right? So I'm saying for your test scores, your mean is 70 and your standard deviation is 10. Okay, now I want you to find the z-score for a student scoring 85. Okay, so again, same thing, we can put all those values in the formula, right? So it'll be the data point minus your mean divided by the standard deviation. Okay, so your z score is coming as 1.5. Now let's try to analyze this z score. Okay, so basically this thing is saying that students score 1.5 standard deviation above the mean. Okay, so I told you, right. So we are trying to find out, right, how many standard deviation away your value is from the mean, right? So you, based on the score, based on the z score, we can say your value is 1.5 times standard deviation away from the mean. Okay, so let's move to the next example. You will have better idea. I have good examples prepared for you. Okay, yeah. So now let's try to standardize the test score. Okay, how will we do it? Let's try to solve it using an example. Okay, now let's say we have again the same thing. Our student's test score is 85, and the class has mean score 70 and standard deviation is equal to 10. Similarly, we can compute the z-score. Your z-score is coming as 1.5. It means your student scored 1.5 times 1.5 times standard deviation above the mean, right? And if the distribution is normal, I'm assuming it to be normal, right? So it means a student performed better than 93.32% of the class. Okay. And how can we say that? This we will study in our upcoming sessions. Okay. How are we calculating this percentage? Okay. Yeah. So now let's compare two data sets. Okay. So now let's say two students take tests in different subjects, right? So his math score is 80 with a mean of 70 and standard deviation of 5, right? Mean is for the whole class and standard deviation that we have calculated for the class, right? And for the science score, he scored 90 with a mean of 80 and standard deviation of 10. Okay, so now let's calculate the z-scores for both the subjects, right? For math is coming as 2 and for science is coming as 1. Okay, so the student is 2 standard deviations above the mean in math, right? And student is 1 standard deviation above the mean in science. Okay, so math score is almost equal to 2, like is relatively better compared to science, right? It means you can say he has performed better than other students in case of maths, right? But he was like in the similar range of all the students if we talk about his science score. Okay, got it? Any doubt here? Any doubt? It's a very
No,
interesting topic. If you
no,
try to visualize it, I can
no.
explain it again. No doubt. Vinay, Ashish, Prashant, anyone here?
It's good to go. And if you want to explain a bit other way, you can explain it.
If you want me to explain, I can.
No, no, it's fine as of now.
Okay.
Explain at the time of visualization in our uh, collaborate.
Sure, sure.
Thank you.
Think I don't. Yeah, I have visualization for this as well. Okay, let's move to the next example. So I told you, right, we can use these scores for detecting outliers as well, right? We discussed, right, if it is greater than or less than -2. I mean, if it is greater than 2, it could be potential outlier. If it is less than -2, it could be a potential outlier. Okay. So here, if we see, we are talking about a company salary, the employee salary in a company, right? So I've just created a data set, right? We have 40K to 100K salary. So mean of the salary is 60K and the standard deviation of the salary is 20K. Okay. So now let's compute Z scores for the outlier detection. Okay. So to detect the outlier, we need a sample, right? So let's pick 100K as the value here, right? So for 100K, the mean is the Z score is coming as 2, right? And for 40K, the Z score is coming as -1. Okay. So typically Z scores beyond ±2 or ±3 indicate outliers, right? As I mentioned earlier. Okay. So for 100K salary, the Z score is 2.0. So it's an extreme value, but not necessarily an outlier because it's almost equivalent to 2, right? But if it is very high than 2, right, or greater than 2, it could be a potential outlier in that case. Okay. But if it is 3 greater than 3 or smaller than -3, right, it is definitely an outlier. Okay. This is kind of a thumb rule when we use Z-score. Okay. So yeah. Now let's move to the notebook and we will visualize the Z-score. Okay. Yeah. And one more time, I want to tell you. So this is the last session for your descriptive analytics or descriptive statistics, right? In the next section, we'll be discussing about the probability. We'll spend almost 2 or 3 classes on probability based on your understanding, right? If you're able to grasp it in 2 classes, we will finish it in two. Otherwise, we'll have one more session for it. Okay. Yeah. Now let's try to calculate the Z-score using the SciPy library first. Again, it's a very simple thing, right? We're using the scipy.stats package, importing Z score. It's the same thing that we have done in the last two examples, right? When we calculated skewness or the kurtosis of the data set, right? So for the Z score, we have a data set, right? We are converting into a numpy.array, okay? Because it accepts in numpy array, the Z score function. Okay, so we are passing this data numpy array in numpy array format to our z-score function, and this will return your z-scores for all of these values. Okay, so for 50, the z-score is -1.40. For 55, it is -1.08. For 100, it is 1.83. Okay, any doubt here?
No,
Okay, yeah. So here if you see it's for 70, right? It's not exactly 0, but I just want to tell you teach you this thing. If your Z score is almost 0 for a particular value, it means you're almost or you are exactly at mean, right? So in this case you are very close to mean, but if it is exact 0, right, means you are at mean. That value is mean only. Okay, any doubt here? Okay. So here again, in this case, we are getting 1.83, but if your, let's say for 100, if your Z score is greater than 2, it could be a potential outlier. Okay. Now let's visualize Z scores in a normal distribution. Okay. How this thing looks like in a normal distribution. Okay. So this is how your normal distributions looks like, right? Okay. So here we have this center axis. This is nothing but our mean, right? In case of because normal distribution is a symmetric distribution that we discuss about, right? We will discuss normal distribution in detail, right? So you can just consider this is like one standard deviation away. This is like two standard deviation away. Anything beyond that can be a outlier. Okay. So anything beyond -2 and 2, right? That is nothing. Like we discussed, right? What is Z score, right? Z score is nothing but how many standard deviation times your stand values away from the mean, right? So here, if we just point out here at -2, it means we are two standard deviation away from our mean. Okay. If we talk about here this point again, we are two standard deviation away from our mean. Here it was negative, here it was positive, right? So anything beyond that, we are calling it as an outlier. Okay. But it could be potential outlier. I'm not defining it as extreme outlier, but anything beyond -3, it means three times standard deviation away, it is an extreme outlier or definitely outlier. Okay. Any doubt here so far? Yeah. So for a normal distribution, there are two assumptions. Okay. Your normal distribution will have mean 0 and standard deviation 1. Okay. We will discuss about the distributions in detail in when we, discuss inferential statistics. Okay. So this is the end of the session. Okay. Finally, like we have wrapped up all the descriptive statistics. Okay. Any question, anything related to any session, you can ask me. And if there are no question, then we can end the session. Guys, you can unmute yourself and ask the question. Okay, great. I guess no questions. Then we are good to end this session. In the next section, we will discuss about the probability. It'll be great if you find some time and read something about the probability. So it will help you to understand it in detail, right? I'll try to, make it as simple as possible for you guys, as I've done it for descriptive statistics, right? But still, if you can, read something about it, it'll be great. It'll be able to help you.
Yeah, sure.
Okay.
Sure.
Yeah.
Yeah.
Okay.
Thank
So
you.
thank you, everyone. Have a nice evening now. Bye bye.